In this episode, we will talk about reinforcement learning training for math reasoning. Today, we're diving into some really fascinating work from the AI team at Perplexity, published just recently, May 5th, 2025. They've been tackling a pretty interesting challenge. How do you supercharge the mathematical reasoning abilities of large language models using reinforcement learning, or RL?
Exactly. And their exploration, it seems, had a clear two-pronged goal. First off, they aimed to really dissect the process. How do you actually achieve state-of-the-art performance in math reasoning using these RL techniques?
Okay. And the second part?
And secondly, which is, I think, equally exciting, they wanted to take those lessons, the hard-won ones, and directly apply them to make Perplexity's own products even better.
Right. So we're getting a kind of front row seat to some cutting edge AI development and its practical side.
That's it. Real-world application.
Okay, let's unpack this then. Their research journey covered quite a bit of ground, and they've shared some really insightful findings. We're going to delve into the infrastructure they built, which is foundational, right?
Absolutely.
Then the crucial role that carefully mixing different kinds of data plays, how reinforcement learning can actually push these models beyond just, supervised fine-tuning SFT.
Yeah, beyond just showing it examples.
And finally, we'll look at why the underlying capabilities of the language model itself matter so much, especially its ability for long chain of thought reasoning.
That step-by-step thinking.
Exactly. And why having a solid starting point from that supervised fine-tuning is, well, incredibly important. It sounds pretty comprehensive.
It really is. Let's start with the foundation, like you said.
Yeah.
The infrastructure. Training these massive models with RL, it's a huge undertaking. So Perplexity needed a robust and scalable framework. They had a few key properties in mind.
Like what? What were they looking for?
Well, scalability was obviously paramount. It had to handle their large models. Training speed was another big one.
Yeah.
Time is money, right?
Always.
And they wanted a system that would let them easily implement new RL algorithms, but also maintain them without, unnecessary complexity.
So, simpler architecture, easier to extend.
Right. And ideally, unify it somehow with their existing supervised fine-tuning work,
Mm-hmm.
like needing a high-performance workshop,
Yeah.
Easy to reconfigure, common tools.
Gotcha. A workshop that's big, has the right tools, easy to organize, and kind of speaks the same language as the rest of the setup.
They looked at a few options, right? NemoLiner, TorchTune.
Yeah, TorchTune, VRL, and OpenRLHF were the main ones they considered back in February 2025.
So what led them to their first choice?
While comparing them then, they initially picked Nemo Aligner as their short-term fix. The big plus was that it already had a pretty complete set of features needed for RL, ready to go, basically.
Okay.
And their partnership with NVIDIA, that obviously provided significant support and optimization help.
But not perfect. He said short-term. Right. Not quite the perfect long-term fit. This setup could be quite involved, apparently, and relying on multiple different software repositories, well, that adds complexity to maintenance.
Makes sense. Powerful, but maybe a bit clunky.
Something like that.
And the other options, why weren't they the immediate go-to?
So TorchTune is actually Perplexity's own SFT framework. Their vision is for it to be the long-term solution for RL2.
Oh, interesting. Keep it in-house.
Exactly. It's got an elegant design. It's extensible,
Mm-hmm.
very attractive. But back then, February 25, it was still missing a lot of the key features for RL training.
Still under development.
Yeah. So the plan is to evolve TorchTune later, add their own custom RL stuff once they've learned more using NemoAligner, kind of a buy now, build perfect later strategy.
That seems practical. Leverage something mature to start fast, but aim for a tailored solution down the line. What about VRL and OpenRLHF?
VRL looked interesting. It had good support for distributing training like fully sharded data parallelism and Megatron LM.
Techniques for really big models.
Right. But at the time, the focus for Megatron LM was more on smaller models where FSDP was often enough. Interestingly, though, they note VRL has developed a lot since then.
So they might revisit it.
Yeah, they explicitly mention they might circle back to VRL. As for OpenRLHF, it's popular in academia, but its reliance on the deep speed backend had scalability limits for the really huge models Perplexity uses.
So not quite up to their scale needs at that moment.
Pretty much, yeah.
Okay, so they've got Nemo Aligner running, eyes on TorchTune for the future. Let's get into the algorithm as the actual learning logic. They mentioned PPO, Proximal Policy Optimization.
A very common one.
Yeah, and this newer one, GRPO, Group Relative Policy Optimization. What's the difference and why focus on GRPO?
Okay, so PPO, proximal policy optimization, it's definitely popular. Widely used for LLM fine-tuning. People like it because it's relatively simple,
But
stable.
there's always a but.
Well, a potential limitation, especially with these really massive models, is its support for tensor parallelism isn't always the strongest.
And tensor parallelism is key for speed on big models, right? Splitting the work across processors.
Exactly, like having many chefs work on different parts of the same huge meal simultaneously. Speeds things right up.
And GRPO is better at that.
That's the idea. Group Relative Policy Optimization, GRPO, it's a modification of PPO that tries to address this. One key thing it does is ditch the separate value model.
The value model. That's the part PPO uses to guess future rewards.
Right. And that component can add significant computation and memory cost, especially at scale. GRPO gets rid of it.
So how does it estimate value then?
It uses a group-based approach. For each question, the model generates, like, multiple possible answers.
A whole batch of them.
Yeah. And then it evaluates these as a group. The advantage, basically, how good an action was for each individual response is then figured out relative to how the whole group performed.
Ah, okay. So you compare each try against its siblings, essentially. Sounds clever.
It is. Gets a potentially more nuanced signal.
But they also said, while it simplifies by removing the value model, it adds its own complexities. Not exactly a free lunch.
That's a very good point. No free lunch here.
Mm-hmm.
Removing the value model is nice, but this group-based thing, well, it brings new engineering challenges.
Like what?
Mainly efficiently generating multiple, often very long sequences for every single input. You have one math question, you might need, say, 8 full answers generated. That needs serious optimization.
Right, that could become a bottleneck fast. So how did Perplexity actually get GRPO working well in their setup? What were the key hurdles?
They made several crucial improvements. First, obviously, they had to implement the GRPO algorithm itself within NemoAligner, code it up.
Cindric stuff.
Then they developed a more robust estimator for the KL divergence.
KL divergence. Kullback labeler? That measures how much the model's policy changes, right? Keeps it stable.
Exactly. Prevents it from going off the rails. Very important for RL stability. They also added something called a format reward.
Format reward, what's that for?
It was designed to encourage the model to structure its output in a specific way. Using these tags, think for the reasoning steps.
And answer for the final answer.
Right. Makes it more interpretable. And they also beefed up the rules for automatically checking the math accuracy, handling both numbers and symbolic stuff better.
So tuning the algorithm and the reward signals, any other techie bits?
Yeah, they worked closely with NVIDIA support to integrate tightly with VLLM.
VLLM, that's the library for fast text generation inference.
Correct. And that integration gave them a hefty 30% boost in generating those multiple responses needed for GRPO. Big win for efficiency. It also helped them track down and fix some weird inconsistencies they were seeing in log probabilities when using TensorRT LLM.
TensorTep LLM being NVIDIA's optimization library. And log probabilities are fundamental, aren't they? Why so critical?
Absolutely fundamental. In simple terms, the log probability tells you how likely the model thought a particular sequence of words was. RL algorithms like GRPO use these probabilities to figure out which actions, like generating specific reasoning steps, led to better rewards.
So if they're wrong,
If they're wrong, the algorithm gets a totally distorted picture of what worked. It's like navigating with a compass that's way off. You'll learn the wrong things.
okay, bad compass, bad results. Makes sense. How do they actually check if their log probabilities were correct? Sounds tricky.
It was a major effort, actually. They set up this rigorous checking process. They compared the log probs from NemoAligner against reference ones they got by running the exact same models using the standard Hugging Face Transformers library.
Okay, compare against a known baseline.
Right. For every single token generated, they calculated the ratio. Nemo log prob divided by Hugging Face log prob. Ideally, that ratio should be 1.0, right? Perfect match.
And was it?
Initially.
Not even close.
The average ratio was something crazy, like 100,000.
Wow, that's very off.
Yeah, indicating a huge discrepancy. So they went through this painstaking debugging cycle, updating converters, changing code, rebuilding software images, the whole 9 yards.
Must have taken ages.
Sounds like it. But they eventually wrestled that ratio down to between 1.0 and 1.05.
Much better, within 5%.
Exactly. That gave them the confidence that the core calculations for their RL training were finally accurate.
That really underscores the deep engineering needed, getting those basics right before you can even trust the fancy RL stuff on top.
Totally.
Foundational.
So with the infrastructure sorted and GRPO finely tuned, what did the actual experiments look like? What were they trying to answer?
Okay, the main goal was to really test how effective their RL approach was for boosting math reasoning. They primarily used the Math 500 dataset for evaluation.
A standard benchmark for math problems.
Right, and their main metric was pass at 1. Pretty simple. Is the very first answer the model spits out correct? Yes or no?
Straightforward.
During evaluation, they controlled generation using a sampling temperature of 0.7 and top of 0.95. These just affect the randomness of the output.
Standard parameters.
Yeah. And because GRPO needs multiple samples per question and math reasoning can be really long, they hit memory issues.
Ah, the dreaded ohms. Out of memory errors. Exactly. Cue to booms. So they had to do multiple rounds of hyperparameter searching just to manage memory effectively. They also mentioned ironing out some minor wrinkles with data loading, when to stop training early, and some odd edge cases with tensor shapes. Little things that always crop up.
The joys of large-scale ML research. What about the prompts? How did they ask the models the questions?
They use specific formats. Interestingly, no system prompts those overall instructions at the start.
Okay, so just the question.
Well, for training, they used what they called training prompt. It framed it like, user asks a math problem, assistant solves it. The key instruction was, first think step-by-step inside think tags, then give the final answer inside answer tags.
Very structured?
Yeah. And for evaluation on Math 500, a slightly different evaluation prompt. It asked the model to reason step-by-step and put the final answer in a LaTeX-style boxed thing.
Helps with automated checking, I guess.
Definitely. Standardizes the output.
And which LLMs were they actually experimenting on?
They focus mainly on the Llama 3 family. Specifically, Llama 3.1 8B Instruct, that's the 8 billion parameter one fine-tuned for instructions.
The common one?
And the Llama 3.1 8B base model, the raw pre-trained version without that instruction tuning. Good, widely used baselines for this kind of reasoning task at that scale.
It makes sense. And the training data, where did the math problems come from?
They pulled together a mix of public data sets with different difficulty levels. For easier stuff, they used GSM-8K, about 7,000 word problems.
Okay.
Medium difficulty came from the standard math dataset, also around 7,000 high school math problems.
Right.
For the harder problems, they used ORZ, Open Reasoning 0. Much bigger, 57,000 examples. And it actually includes the whole math dataset plus other complex stuff.
It was superset.
Kind of, yeah. And also Numina-Math, another large one, about 250,000 problems after filtering, also classed as hard.
Wow, a lot of data.
Yeah. And they mentioned the answer labels for most of these came from a bigger model, QWQ32B Preview and R1. For the final testing, as we said, Math 500, this mix is important.
Right, covers the spectrum. Okay, models, data. Now, the training process itself, finding those right settings, the hyperparameters for GRPO, sounds critical.
Oh, absolutely crucial for RL. They started by focusing on the GSM-8K dataset, the easier one, to explore the key settings first. They systematically tried different learning rates, 88, 1E7, 3E7, 5E7. That controls how big the adjustment steps are.
Got it.
And they paired those with different KL coefficient values, 0.1, 0.01, 0.01, 0.001. Remember, KL helps stabilize things.
Right. So what worked best?
They found that a learning rate of 3E7 seemed to give stable performance pretty consistently, so they adopted that for the main experiments. And interestingly, lower KL values often worked better. In the end, they actually found it best to remove the KL term entirely for their final runs.
Really? No KL stabilization?
Apparently, they suspected that higher learning rates made the model converge too fast, maybe locking into simpler solutions and not developing that deep step-by-step reasoning needed for the hard problems.
Huh. That's fascinating. Sometimes slower, smaller steps are better for complex learning. What else did they tune?
Temperature. The sampling temperature during generation. They tried a range, 0.7 up to 1.3.
Remind us what temperature does again.
Controls randomness. Lower temp means more predictable, likely output. Higher temp means more random, diverse, maybe less coherent output.
Okay. And this sweet spot.
They landed on 1.0 as the default. Seemed to balance training speed and final accuracy well. Higher temps often led to instability. Training just wouldn't converge properly. Lower temps converged faster initially, but then the model kind of hit a wall, plateaued too early on the validation set.
Finding that Goldilocks zone and the rewards, how did they tell the model it was doing well?
They mainly tested two rule-based rewards, inspired by work from DeepSeek. First was just accuracy reward. Simple. Did the final answer match the ground truth? Yes or no?
Straightforward.
Second was the format reward, specifically encouraging that think-answer structure from the training prompt.
Okay. Which did they use in the end?
For the main RL runs, they settled on the 3E7 learning rate, no KL coefficient, temperature of 1.0, and they relied only on the accuracy reward.
Interesting. So they dropped the format reward for the final push.
Seems that way, yeah. Just focused on getting the right answer.
All right, I've got the setup crystal clear now. Let's get to the main event, the results. What happened when they applied this RL fine-tuning?
Okay, the key results are shown really nicely in a figure they included. It compares the accuracy on Math 500 after RL tuning on that hard ORZ dataset. And crucially, they started the RL from 3 different points.
Which were?
First, a model already warmed up with supervised fine-tuning on ORZ itself. Second, a standard off-the-shelf Llama 3.18b instruct model. And third, the base Llama 3.18b, the raw pre-trained one.
Comparing those starting points is key.
Exactly. And the results gave them 2 really significant findings.
Okay, lay them on us. What are the big takeaways?
Takeaway number 1. Reinforcement learning, when done right, significantly boosted the math reasoning skills across the board. For all the models they tried, they saw improvements not just in accuracy of the pass at one score, but also the models generated longer reasoning chains, on average.
So better answers and more detailed thinking.
Pretty much. And impressively, their best result, which came from RL tuning the model that was already SFT warmed on ORZ, hit 1.70 accuracy on Math 500.
70%. That's really strong for Math 500, isn't it?
It is. They specifically point out that this matches state-of-the-art results from other research around that time. So their approach was definitely effective.
That's a major validation. What was the second key insight?
The second critical finding was just how huge an impact prior exposure to long chain of thought data had.
Whether from pre-training or that SFT step.
Exactly. That prior exposure dramatically accelerated the RL fine-tuning process and significantly enhanced both its effectiveness and efficiency.
How so?
Looking at their graph, the model that got the SFT warm-up on ORZ first, it started the RL phase already at a much higher accuracy level.
Okay, a head start.
Big head start. And it also ended up plateauing at a considerably higher final accuracy compared to the model starting for the vanilla instruct or base checkpoints.
Wow. So SFT helps it learn faster and reach a higher peak during RL.
That's what the results strongly suggest. They even hypothesize, though. They say it's not fully proven yet that SFT might not just make RL more efficient. It might actually raise the upper limit of performance you can ultimately get from RL.
So it's like teaching the model how to think step by step first makes the RL refinement much more powerful. Makes intuitive sense, really. Easier to improve a skill than build it from scratch.
Absolutely. A good foundation matters.
Now, they didn't just stop at results. They dug into why some things happened, analyzing phenomena they observed. Let's talk learning rate again. Sounds like a nice edge.
It really does. Their experiment showed it's this crucial dial, controlling learning speed but also stability. Predictably, too small learning rate, progress was just slow. But too high.
Problems.
Yeah, too high, you get quick gains on the training data initially, but then things often become unstable, sometimes leading to that model collapse they mentioned.
Where performance just tanks.
Right. Quality deteriorates. Maybe you get these ridiculously long, rambling reasoning chains. They found that middle ground, 3E7, was the sweet spot for them. Stable progress to a good level.
And 1E7 was just too slow to converge in their experiments.
Exactly.
Okay, this model collapse. Sounds pretty bad. They identified 2 main types, self-repetition and end of sequence. Let's start with self-repetition. You mentioned the format reward might have counterintuitively caused issues here.
That's what their analysis suggests, yeah. Remember, the format reward encouraged at least one think and one answer block.
Right, for interpretability.
Well, while training rewards sometimes looked okay with this, they hit this weird side effect.
Yeah.
The model started repeating empty format blocks after it had already given the correct reasoning and answer.
Like think, answer, not answer, answer, think, answer, over and over.
Exactly like that.
Yeah.
Just nonsensical repetition, clearly a breakdown.
It's definitely not what you want. What did they try then?
They tried tightening the screws. A stricter format reward. Exactly one think, then exactly one answer.
Did that fix it?
Nope. Counterintuitively, it seemed to make it worse. The empty tag repetition continued, and the overall answer accuracy actually dropped.
Wow. So the stricter rule backfired.
It seems so. This led them to suspect the format reward itself might be causing this collapse, so they tried experiments without it entirely.
Which then led them to observe the other type of collapse, end of sequence.
Precisely.
And that sounds like it's about hitting the maximum generation length.
You got it.
Yeah.
End of sequence collapse happens when the model just keeps generating until it hits the max token limit you set. If all the generated responses for a problem get cut off like that, the RL system gives them all 0 reward, right? Because they're incomplete.
Even if the reasoning was good up to that point.
Even if it was perfect. Zero reward means zero advantage signal, zero gradient update. The model gets stuck. It can't learn to improve because it's only seeing failure due to length limits. Exactly. And they saw a clear correlation. As the rate of rollouts getting cut off increased, the overall trending reward dropped. They also noted this isn't unique to them. Other research on long COT reasoning has seen similar issues. It seems to be a general challenge.
So the model gets penalized for being too thorough, essentially. Great reasoning, but you talk too long, 0 points.
That's a perfect analogy.
Yeah.
They even tried reward shaping to specifically control length, discourage long outputs.
Did that work?
It kind of worked to shorten things, but it also seemed to mess up the learning of the actual reasoning. Math accuracy went down.
It's another trade-off.
Yeah, and it ties back to that idea about the base model needing some COT ability. Without it, RL might just push for length without substance, leading to this collapse.
It really keeps coming back to the importance of that base model capability. They did an ablation study on that too, right? To isolate its effect?
Yes, exactly. To nail down the impact of prior knowledge, they did this ablation. They took the base Llama 3.18b.
And fine-tuned it first with SFT on different data sets.
Right. SFT on ORZ, the hard one,
Hmm.
Math, medium, and GSM-8K, easy. Then they took each of those differently prepared models and ran the same RL fine-tuning on ORZ on all of them.
Allows a direct comparison of starting points.
Precisely.
And the key insight from that comparison.
The results were pretty clear. Starting with a model that had already seen a diverse mix of difficulty levels during SFT, significantly boosted the RL training on the hard ORZ data, both efficiency and final performance.
So that well-rounded SFT phase, exposing it to easy, medium, hard problems, sets the stage much better for RL.
Absolutely. It gives RL a much better foundation to build upon for the really advanced reasoning. This also got them thinking about future work on curriculum learning.
Curriculum learning, like starting easy and getting harder.
Exactly. Either within one domain, like math, starting simple, increasing complexity, or maybe even across domains, get instruction following solid first, then tackle reasoning. They mentioned the QWQ32B model they used for labeling probably benefited from strategies like that.
Makes sense. Build foundations first, like how humans learn. Finally, they looked at rollout length, scaling how RL affected how much reasoning the model produced. What did they see there?
Well, they saw the general trend others have seen. RL tends to encourage longer rollouts, longer reasoning sequences.
Just makes them chattier.
Not quite indiscriminate chatter. Their analysis suggested it's more nuanced. RL seems to be trying to find an optimal reasoning length based on the model's starting point and the problem difficulty.
How so?
For instance, starting with the raw Llama 3.18b base model, which hadn't seen much long CUTI and gave short answers, RL made it generate much longer reasoning chains, and that helped accuracy.
Okay, needed more steps.
But when they started with that same base model, but after warming it up with SFT on ORZ, which already made it generate long chains, the RL step actually seemed to suppress the length a bit, while still increasing accuracy.
Huh. So it learned to be more concise but more accurate in that case.
It seems that way. It's like RL isn't just blindly increasing length, it's tuning it to what's most effective for problem solving, adapting based on the model's initial tendencies.
Finding the right amount of thinking, not just more thinking.
Exactly. A more sophisticated adjustment.
This has been, wow, a really deep dive into Perplexity's work here. Hugely insightful. So summing up the key takeaways, RL looks really promising for boosting math skills in these models.
Definitely promising. But as their research makes abundantly clear, it's absolutely not a magic bullet. You need to be really careful.
Right. Careful about the infrastructure.
The algorithms like GRPO, knowing their quirks,
How you mix your data in pre-training and SFT.
and being super aware of potential failure modes like those model collapse issues.
And that foundation piece seems paramount. A base model that already has good long chain of thought skills is critical for RL to work well in this domain.
That's maybe the critical conclusion. And their ongoing work moving to TorchTune, tackling model collapse, shows this is still very much an active research area.
Absolutely. So as we wrap up this deep dive, here's a final thought for you, our listener, to maybe chew on. We've seen these detailed insights about training LLMs for complex math reasoning. How might these lessons, these challenges apply to other complex reasoning tasks, or maybe even totally different fields where we're pushing AI limits? What other factors, beyond just data and algorithms, might be the really critical pieces needed for those next big breakthroughs in AI capability? Something to think about.